All right, so we're talking about a couple of different processes that are designed to kind of achieve the same thing, and they both do this in the context of a implant bone interface. Plasma spray processing is a relatively old technique. It's used for a lot of other things besides implants, but we'll talk about exactly why this technique is useful and what it does to the hydroxyapatite that we use it to process. And at the same time get some insight in terms of what the surgeons have to do when they deal with these situations. And so it's instructive to realize that in some ways surgery is the same thing as wood shop, basically. So that's kind of what some of these things address. And the other side of the coin is something that's much newer and much more modern, but again, it tries to achieve the same thing, which is load transfer between an implant and the bone around it, and that's trabecular metal. So before I talk about those, I'm going to talk about this paper, the entire journal. Sorry, so this is the paper I'm going to be assigning. Oop. Come on down. Powder injection molding of metallic and ceramic hip implants. All right, and I saw this and I thought, wow, this is perfect. And I was trying to figure out what should I do with it, and now I know. So what I'll do is I'll post this on the website, or I can email it to you. Your preference? Either one's fine. Either one? Okay. All right, and then I'll just ask you specific questions. And if you look through this paper, it's like they patterned it after my class, so it's pretty amazing. So anyway, so I'll just try to ask you some relatively specific questions. Short answer, 2-3 sentences, hopefully not a paragraph, something like that. All right, and it'll be, I don't know, 1 or 2 pages. All right, but it just requires you to read and understand. All right, and in this context, you'll see that there's a ton of things that are identical to what we've been talking about. But these guys are looking at, it's sort of artificial, making hip implants out of injection molded alumina on the left and injection molded 316L stainless steel on the right, neither of which is actually used anywhere. All right, but it goes through some of the ideas and processes and conditions and so forth necessary to make all these things. And then they follow that up, talking about debinding and sintering and so forth, and then some microstructural analyses here and there. They have a cracking issue, we can talk about that. They also do some numerical simulations, which are interesting, but not necessarily going to talk about. And then some aspects of strength as well. Okay, so it should be pretty straightforward. All right, it's not designed to be onerous either for you or for me. So, and that's kind of what I'm planning on doing. All right. What?
It's like guided questions.
Yeah, guided questions. Yeah, right. So here are the questions. You can find the area of the paper that has the information in there, and then just tell me about what they did and why they did it. That's going to be things like that. Okay. All right. So it's a very relevant paper because it's supposed metal injection molding and ceramic injection molding and making biomedical components and worrying about things. All right. So it's really dead on in terms of the stuff we've been talking about. All right.
Do you have a timeline on when you think it'll be due / actually signed?
I think a week from today would be good. I mean, I don't want you to drag it into the exam prep end of things. So I'm going to try to get it over with. It really should not be hard. I mean, compared to taking a test, this is going to be straightforward. Okay. I mean, really not. Exam being all about the scheduled, right?
Yeah.
Okay. All right, so we're all good there. As far as I know, no one's objecting to that, the Wednesday. All right, and so getting back to the topic at hand, we're talking about plasma spraying initially, and it turns out that what's really important to us here in the context of biomedicine is plasma spraying of hydroxyapatite. And plasma spraying is used to make aluminum silicate coatings and things like that for washing machines, all sorts of crazy stuff. And then a lot of aerospace applications, some of which we'll talk about a little bit here. But in the context of what we're doing is we're trying to produce coatings of hydroxyapatite. And so this is kind of that tyranny of shape thing I always bring up, because we have implants that are pretty good. They're titanium, all right? And we know titanium gets along well with bone, but it could be better, all right? And so what hydroxyapatite does, it brings to the table its own capabilities in vivo and applies them to titanium. And this helps address a big issue in that when a surgery is done, I don't know if anyone's ever seen a hip implant surgery or a video of a hip implant surgery, all right, it's pretty brutal, all right, there's not a whole lot of grace to it. You cut off the top of the femur and then you ream out the inside of the femur and make a hole for this implant. And so it's Air Tools, Black & Decker, it's not precision scalpel medicine at all, all right, and so what we're doing is we're taking, as I talked about last time, a relatively standardized implant and putting it into a wound which is far from standardized, all right? So there's the fit is not good at all. But what hydroxyapatite does is allows some of that to be overcome by essentially applying food for new bone, okay? And so how do we get the hydroxyapatite there, and what do we worry about? Plasma spraying is the technique, and hydroxyapatite is the target. And we like hydroxyapatite because first off, it's bioactive and bioresorbable. So in that sense, it's providing bone this food it needs. It provides calcium and phosphorus for the body to say, oh, I know what to do here, and make bone. And so it does that. There are a number of different specifications. Hydroxyapatite in the US, hydroxylapatite in the UK, and then there's a variety of information out there. It's called the original bioactive ceramic. Anybody know why? All right, that's what your bones are made of, hydroxyapatite. Carbonated hydroxyapatite, but it's still hydroxyapatite. So the body has this very defined set of techniques for dealing with hydroxyapatite because it does it all the time. All right, and one of the reasons why hydroxyapatite is kind of a privileged material is that the body has these mechanisms in place. You throw stainless steel in the body, it doesn't really know what to do with it. You throw polylactic acid in the body, it kind of sort of knows what to do with it. But you put hydroxyapatite in the body and it generates calcium and phosphorus, and the body says, okay, I'm going to make bone. All right, and that can overwhelm a lot of the other things, like the attempt to try to kill any foreign invader. You says, oh, I'm making bone, I'm not trying to kill this, I'm trying to make bone, because it has to manage calcium and manage phosphorus. You can take hydroxyapatite and stick it in your bicep where bone has no business being, and the body will generate bone around that inside your bicep. Okay, so it's just like an automatic response to the presence of hydroxyapatite. So in this context, though, we're making use of it in a better way than putting it into your bicep. So anyway, up to 50% of bone by weight is a modified form of hydroxyapatite. It's carbonated, calcium deficient hydroxyapatite, the main mineral of which dental enamel and dentin are composed of. And this response the body has to say, oh my God, I got to make bone, means that that initial compatibility is excellent. All right, so it improves upon what titanium and anything else already has as far as biocompatibility, and makes it even better. All right, and partly that, as I said, it's kind of overwhelming the body's normal desire to try to kill anything that doesn't belong there. All right, by saying, oh, well, don't stop killing it, let's turn it into bone. So dental implants, orthopedics is what we're talking about on titanium, maxillofacial surgery, and bone filling powders, which we'll also talk about a little bit. You guys all got the and this is an example of the kinds of coatings that are used, and you should be able to recognize many of these things. And so we have the acetabulum, a form of ephemeral implant, a different form of ephemeral implant. All right, and this is a third form of ephemeral implant, just stops. All right, so you can see that rather than having nice clean bone, which you happen to see in this one version of it, you add these white coatings or grayish coatings, which is a combination of hydroxyapatite white and the titanium underneath it gray. All right, so you put those two together and you get these different visual versions of coatings, and they're all there and they all have the same purpose, to generate bone at that interface, either the acetabulum or the femoral implant. And you can see it's kind of conditional. You know, this particular one, that's nice and bare. All right, and we'll talk about why you get it up here. And you've already talked about this somewhat. You want bone ingrowth in some areas and not necessarily bone ingrowth in other areas. Okay, and then this is I'm not really sure exactly what that is because it's obviously a screw, but it's a gigantic screw. So I don't know if it's an implant for an elephant or just something they're messing around with or what. But this is also showing you that even for something as trivial as a screw, a bone screw, you still have to address this issue of trying to get ingrowth between the metal and the thing that you've just screwed into the bone. All right. So you create this defect and you try to fill it at the same time, and then you want this rapid osseointegration, that word I used last time, that generates a strong mechanical interlocking. All right. Yes.
So if your implant breaks and a shard of it gets lodged in your quadricep or something, it contains hydroxyapatite. Their bone potentially grow there too.
Yeah, if that happened, if you got shot with a bullet of hydroxyapatite, and then yeah, it would make bone around it.
They have to be really certain whenever they replace one of those, they have to get everything out, or one snaps to get everything out.
Yeah, right. It's not normally that big of an issue, but yeah, I mean, yeah, it is. It is. Like I said, if you implanted it in your bicep, you'd make bone in your bicep, and eventually the body would remove it because it doesn't belong there. But it's just an automatic response to the presence of hydroxyapatite, or calcium and phosphorus. Primarily calcium is so this calcium homeostasis is really important because it can poison various cell processes if there's too much calcium in one area. So the body has to turn it into bone in that area. It has to make something that stores that calcium or turns it into bone, one or the other. Okay. Any other questions? Hydroxyapatite, if you look at the old literature, they used to call it bioinert. And I think I talk about this, but they at one point in the 50s, 60s, they were trying to make human femurs out of solid hydroxyapatite. And then stick that into, I don't know if they put it in people or not, but the problem is that the body sees hydroxyapatite, even if it's nice and dense and flaw-free, and the first thing it does is it tries to eat it and make flaws in it because it knows what to do with hydroxyapatite. All right, and so that old style approach was doomed to fail because the body will make defects where there aren't any because it knows what to do with hydroxyapatite. Okay, and it's just this automatic response to its presence. And this is an example of, and this is not an old product, this is a currently used product called Urosert, and we'll talk a little bit more about that in a minute. But this is just bone filling material. So if you have a defect in the bone, this gives you an idea of what hydroxyapatite does. You put these little shapes, which are designed for certain types of defects, or more likely the stuff over here on the right with tiny little blocks, and you put those in the defect, and the body says, oh, okay, well, these two areas of bone have a big hole in them. I've just put some food in there, so I'm going to generate bone, and at the same time it tries to fill that defect in the bone. All right, so it's just a knee-jerk response, which happens here in this context in a useful way to try to generate bone where it needs to be. Up a little bit. So this Urosert is an example of that. So it's calcium with some tricalcium. It's hydroxyapatite with some tricalcium phosphate in it, deliberately. All right. And this is all very interesting, but if you dig into this, you'd see that hydroxyapatite is a part of a much larger family of calcium phosphates. And so we'll talk about a lot of these. This tetracalcium phosphate, tricalcium phosphate, monatite, which is not very useful. But the thing that we need to note here is that hydroxyapatite is a line compound. Calcium to phosphorus ratio is equal to 1.67. Oops. All right. And so it only occurs pure hydroxyapatite at one specific point on the phase diagram. All right, everything else is not the same. And that's significant because it means that you need to have precise control if you want pure hydroxyapatite. Now, the thing to note here is what happens if it's not pure. All right, and so if you go in the direction of too much calcium, you're getting calcium oxide. If you go in the direction of too much phosphorus, you're getting this tricalcium phosphate. Okay. Does anybody know anything about calcium oxide? Any familiarity with that? So we put calcium oxide in water, what happens to it? Anybody? That's calcium carbonate you're thinking of, but that's good catch. But calcium oxide in water turns into calcium hydroxide, which generates a pH of 12. Okay, so that's not good for the body, which should be pH 7.4. So you put calcium oxide in the body and make calcium hydroxide, pH of 12, things start dying pretty quickly. And so we definitely, if we're going to make an error, we definitely don't want to make the error of too much calcium. On the other hand, if we make the error of too much phosphorus, we make tricalcium phosphate, which, as it turns out, first off, doesn't give you a pH of 12, doesn't dissolve quickly. It breaks down. It's more bioactive than hydroxyapatite, so it's a good thing to have. You know, so all hydroxyapatite that I'm aware of is intentionally made with a slightly rich phosphorus content, because you can't hit that exact ratio very easily, but you can make it a little phosphorus rich and you're safe. Okay. So this is the lay of the land, and so what you do then is you walk out of my class, get in your car, and get into a terrible automobile accident on an I-71, and your bone looks like this. Okay, I think that's that's the femur. Yeah, so that's a human femur that's been in an obviously terrible accident, and if Nick was here, I would say a terrible, disfiguring skateboard accident, and your bone looks like this, all right? And obviously it needs work, okay? So it's not just a simple fracture like my arm, it's more missing bone that's been fragmented and had to be vacuumed out during the surgery to recover from your terrible skateboarding accident. And what they also do is another form of biomaterial. So this is stainless steel. This is a plate that's being used to hold the two pieces of or the multiple pieces of your bone together, and these are bone screws that are holding those things together as well. And so it's really Black & Decker. All titanium, very high tech, but very necessary. But the issue here is you've got this space here. Whoops, come on. This space here that needs to be filled. All right, and so what surgeons will do is they'll take that urosor and they'll literally take their thumbs and just stuff it into that cavity and sew you up. All right, and what the body does weeks to maybe months later is it takes that fuel and generates bone in the gap, and the body takes that new bone, structures it correctly. Eventually it can bear load, and maybe someday they'll take that plate out of your leg if they want to. Maybe they'll just leave it there. So that's the beauty of this. Okay, and so this is a very well defined piece of medicine, and this material has a very important role in that concept alone. So these are, as it says here, what are called biphasic calcium phosphates, and by that they mean TCP plus HA, those two together. All right, any questions about that? And so again, this is tricalcium phosphate. There are alpha and beta forms. The alpha form is preferred, and it's considered a bioresorbable more quickly than HA, but you don't make it out of pure TCP. It's still a lot of HA in there as well. So it's the right moderate amount of these two phases. Okay. Other forms of hydroxyapatite, tetracalcium phosphate. It resorbs too quickly. We don't like it. We like the hydroxyapatite. There's two different ways of portraying that formula. Relatively bioinert, but not really bioinert. The pure bulk form, which is very rarely used. All right, I can't think of an example of that I've seen in current human medicine. It's a major component of biphasic calcium phosphates, which you just saw in the case of urosor, and it's the main component of plasma-strate hydroxyapatite in terms of coatings on titanium implants. And this is the dominant form in human medicine, as these coatings on these titanium implants, far and away, both weight-wise, volume-wise, and numerically wise. One thing, and that it depends on how much background you've seen in this area, they call these cementless total hip replacements. Does anyone know what cement refers to in the context of hip implants? All right, they didn't.
PMMA?
Yes, exactly. So they didn't use the cement from your sidewalks. They used PMMA with some hydroxyapatite and other things. And this is all part and parcel of the Black & Decker side of putting something into your hollowed out femur. What they used to do is they would inject cement into the femur, and then they jam the femoral implant into it, and that cement would hopefully fill the space between the bone and the implant. All right, that's how desperate they were, because it just wasn't growing into the implant as well as they wanted it to. And that was like the 60s to late 80s version of hip implants. So it was used for a good long time. Problem was is that this stuff would basically polymerize in situ. All right, the PMMA part of it and other parts would polymerize and give you this really hard shell, and it would integrate mechanically with the bone around it and integrate with the implant as much as well as it could. All right, and hopefully transfer load. And the problem they had with it is that over time this cement would crack. All right, and when it cracks, you get fragments rubbing around. Titanium gets rubbed on. They would open people's legs up, and there's this black cloud of titanium particles coming out of it, and so it was nasty stuff. So they went away from that, like I said, starting in the late 80s, and went to this as a way of replacing that technology. Okay, and so if you ever see that word, that's what that refers to, is this cementless implants. Any questions about that? All right, so how do we make this stuff? And again, this is one of those tyranny of shape things, in that we have this ceramic, and as you should know by now, it's really hard to shape things out of ceramic. Ceramic injection molding is fine, but making something that would sit on the outside of a titanium implant, which is doing all the work, all right, of mechanical load, would be very difficult. And so what we use is this plasma spraying process. Pure hydroxyapatite powders are injected into a high temperature, greater than 2,000 degrees C plasma flame region. So we think of plasma as the fifth state of matter or whatever it is, or something out there about that. And so it's very, very hot. And they are accelerated toward a substrate, which in our context is titanium or thialuminide, usually porous in some way, and impinge onto a surface to form a coating, at least ideally form a coating. And it produces coatings with good mechanical properties. Now, I'm not going to say it's not load bearing like the implant is, but it's good enough. And when I say good enough, it means that if you jam it into someone's femur or you screw this into someone's jaw in a dental application, the coating does not flake off. All right, that's the key aspect of this. You're not really saying, oh, we want you to hold on to a lot of load. We're just saying, give us the food, don't flake off and end up in the wrong place. All right, so good enough mechanical properties. So don't think you're ever going to do something that's load bearing in this context. And so this is just showing you, well, first off, this is what one of these things look like. And so it's making this plasma, these huge increases in temperature in a short distance. And what's happening inside that brilliant arc is this process of injecting in argon and hydrogen. So hydrogen is our fuel that gets these things to these really high temperatures so quickly. We also have to, very importantly, bring in water, all right, because this is hydroxyapatite, and the body is looking for hydroxyapatite. You're going to 2,000 degrees centigrade. It should make sense to you that one of the first victims of these high temperatures is the hydroxy component of hydroxyapatite, OH. It's not going to stay around very much at 2,000 degrees. So you bring in water to try to make it stay, to force it to stay on the hydroxyapatite. Otherwise, it just becomes oxyapatite, which is not terrible, but it's not what we want biologically. All right, it degrades too quickly. So that's important, and at the same time that's happening, we are also bringing in the good stuff, the powder, being injected into that jet. And again, this is ridiculously high temperature stuff we're talking about. So we have the anode and cathode to help spark this thing and help get the temperature up along with the hydrogen fuel. And these solid particles that we bring in that are shown here, all right, so big chunky pieces of hydroxyapatite go into this jet, and they become at least partially molten, usually not 100% molten, but at least partially molten. And eventually they impact on the surface in what's called a splat. And if you read papers in this area, they talk about splats. Doesn't sound very technical, but that's just the best way of describing them, splats, because they start out as individual particles that melt, and they hit the surface and they splat onto it. All right? Any questions about that so far? All right. And so what we've got here, a couple of good movies that talk about the context. And the context is you're making a coating on a complex three-dimensional shape. And in a perfect world, the coating would come in from all directions all at once and coat that entire shape in one uniform thin film, all right, continuously. But the reality of it is shown here, in which that part spins, and when the torch comes down, at some point, all right, and makes traverses on that part as it spins. So this is the infiltration over here, and this is how it's done. And so what you're doing is you're treating this thing, not all at once, not from all directions, not iso anything, but it's coming in and producing these coatings on that surface. And so that's the reality of it is, and this is a little longer movie, which kind of makes a couple of points that I want you to hear. All right, so APS materials. And let's see, I think
for the past 30 years.
Yeah, Steve Shaw,
APS
production
has been the
manager.
leader
So this is just showing you where Steve Shaw works and all the
coatings
machines
for the
that they
medical
use
implant
to
industry,
achieve these types of
using a
coatings.
proven
And now you
technique.
see that at scale.
Titanium
Same
coatings
thing,
are applied
plasma
to
flame, treating a whole bunch of
surfaces
them, they're
the implant
spinning.
that mate
And then
direct
this guy is
to
doing
the
things
bone.
kind of
We
manually,
apply
he's making
special
coatings.
titanium
And this is
coatings
showing you the
to
goal
dental
here,
and
the
bone
implant,
implants.
which is
So existing
titanium,
bone
and we
actually
want bone to
grows
grow
around
into the
and
implant.
through our
But if
coatings.
we bring in
That helps
hydroxyapatite,
provide the implant.
then the boning grows more quickly and more
Hydroxyapatite
efficiently into that
coatings
surface.
provide
All
an
right.
osteophilic
So again,
surface
you have
that
multiple samples all
increases
being
bone growth
treated at the same
response
time,
provides
and
a
acetabular
superior
cups as
bonding
well.
surface.
All right, as opposed to
The
just
end
bare
result
titanium.
is a coating with
And,
high
the
tensile
process
and
again.
fatigue strength that can
And
be
he's
used
just showing you
on
how
a wide
parts of the implants
variety
are being coated
of orthopedic
and then created
implants.
for manufacture.
We pride
Okay.
ourselves
So these are
on
both
our
good moves,
ability to provide for the customer the best.
And Steve looks like a typical engineer, so give him credit for that. Yeah.
It's kind of like a terminology question. So hydroxyapatite gets remodeled in the body, right? But then you said tricalcium phosphate gets resorbed in the body. So what's the difference between those two?
They both get resorbed. So they are both broken down into calcium and phosphorus ions, and the body takes those and converts those into natural bone. So neither of those is actually bone itself. They're both sources of food for bone to form. TCP breaks down to calcium and phosphorus more quickly than HA does. Okay. So yeah, we don't bond bone to bone. We create new bone where it wasn't before using the food that these calcium phosphates provide. Okay. Any other questions? And as I said, in vivo it's carbonated hydroxyapatite, which is totally different from what we put in the system. Okay. Yeah.
How does you eat hydroxyapatite?
It will probably dissolve somewhat in your blood, and you'll get a little bit of calcium and phosphorus in your diet. It won't make bone in your gut, no. Any other relevant questions? Yeah, that would be bad. I mean, if you ate enough of it, you might get some bone growing in your intestines, but you probably have to eat quite a bit to get it to stick there. Anyway, so this is the process as shown here, and so we have this flame putting these splats on the surface, and you already saw some of the downsides of this, and that it's done in a sequential manner rather than all at once. And aspects of this that make it complicated. First off, so we have, this is kind of a time zero snapshot of these droplets arriving on this surface and integrating with this titanium surface, and they're trying to show some type of roughness of the surface that might be already porous in some way. And the hydroxyapatite hits that surface, and when it does so, it's hitting a relatively cold, maybe even room temperature surface, and so it sees cooling rates of like 1,000,000 degrees a second or some crazy number like that. And so what can happen as that process has occurred is you can get some amorphous calcium phosphate. Come on. Here. Drawing a little less teeny. Come on. Amorphous. Come on. There you go. All right. Because that hit that very cold surface first. All right. And this is something that they do with metal. And they have this amorphous metals. It's a big deal. It's like cooling at 1,000,000 degrees a second. You can turn titanium into amorphous titanium if you cool things off fast enough. It's just the way it works. And then the second drop arrives, and it's seeing this first splat was already there, and so now the cooling rate is not the same as the first one because it's not in direct contact with that cold metal. All right, it's in contact with a relatively hot droplet that already arrived there first. All right, and so this could be 100% crystalline. I'm not going to speculate, but it could be 100% crystalline. For some reason, this is not writing very well today. Man, might as well use my finger. All right, and so we can have amorphous and crystalline next to each other. And the problem is that while the crystalline is good, the amorphous can dissolve more rapidly. That should make sense to you. Under the same stresses, it's easier to dissolve something that's amorphous than something that's crystalline. Okay, and so that is a complicating factor in this scenario. We do want, of course, adhesion. We want that roughness there to make things stick to the surface really well, because as I mentioned a minute ago, shear as these things are inserted into tissue, particularly bony tissue, is a problem. And so we have what's called mechanical keying or interlocking or anchoring, which if the surface is already porous, titanium is really straightforward because there's lots of holes for it to go into. You get diffusion bonding, in which case there's a direct interaction between oxides basically on these surfaces. And then you have the other types of bonding, most of which aren't that helpful. Van der Waals forces, we talk about those a lot in polymers, but in this context they're just really not as strong as mechanical and diffusion bonding. But all these things occur. But as you can see here in this other cartoon, it's a complicated process. It's an ugly process down at the level of microstructure. Okay. So we have this picture in our minds of this nice uniform film, but the reality of it is, because it's a violent process that's not particularly well controlled, things are hitting at high speeds, it's going to make an ugly product from the standpoint of where we'd like it to be. All right, and so this is just showing you another version of that in which these droplets are making an impact. We have some evidence of, first off, it says grit blast interface, which sounds really crude, but is actually what they have used for many years for some of these implants. You take alumina, not sand, blast it with alumina, clean off that surface and generate roughness, and then this plasma coating can interact with it more efficiently, giving you that mechanical keying, that interlocking that you're looking for. And so what you see, though, in this context is some areas are made of individual splats, and you can see the fact that one arrived on top of that. Sometimes it doesn't splat at all because it came through the jet and didn't get as hot as it should, so you can have particles buried in there, and that's all happening on top of that. So it's a very kinetic process, as opposed to the thought you might have of making a nice uniform dense layer. And this is just showing you some examples in cross section. This is silicon carbide. So yeah, you can plasma spray silicon carbide, which is pretty impressive given the melting point of silicon carbide, and put that on a substrate. And you can see in this context there are pores present. There's an interface present, so it didn't really bond that well. And this is some examples of, let's see, that is a ceramic. I think it's hydroxyapatite on some other layer. Again, pores present. Again, you can kind of see defects at the interface. And then for this one example of a plasma sprayed metal, you can start to make out what we just saw in that cartoon, which is the tree ring effect of this. Every layer leaves its evidence there as they hit, cool off, and then another droplet arrives maybe later as this thing's spinning around, all right, and you get this type of layering effect. So it's like tree rings, essentially. You can tell what the thermal history of the implant is by looking at its microstructure. Okay, so unfortunately, in this context, ATEC can decompose, even if we put moisture in it, but if we take the moisture out, it definitely decomposes. Rapid cooling generates amorphous calcium phosphate, and we can make a variety of other types of calcium phosphates, usually not in large quantities, but it is possible because of the complex thermal history of the system. And it's also messy, as I made clear already. Difficult to control, composition of microstructure can vary, cooling rate at the surface cannot be the same as away from the surface, all right? So you can get amorphous calcium phosphate forming. And then different vendors make different products, basically. Okay, and it sounds bad. It's not perfect, but again, this is just providing food for bone. It's not bearing load. Like that's what the implant does. It's bearing load, so it's just a coating, and it just needs to stick pretty well. So it's not that demanding, but it is sort of a concern because you can get decreases in resorption resistance and reduced in vivo performance. You have all these layers involved, and the layers can do funky things. Again, the number of torch traverses is visible in the microstructure, as is shown here. This is an alloy coating. You can see the tree ring history of that coating and how it was deposited. You can probably count the number of passes by looking at that surface. But then where things can go horribly wrong is where we have produced our HA coating. From the outside it looks good. It's on Ti 6.4. That's wonderful. But you have this interfacial debonding when the amorphous calcium phosphate dissolves out. Okay, so that means that there's a weak point where you want it least. All right, so this could be sheared and perhaps peel off, and then you don't get your bone ingrowth because hydroxyapatite is no longer associated with the implant itself. All right, any questions about that? Hopefully it's pretty straightforward. All right, and so moving on to something else entirely, porous metals. And this came about because, as I mentioned at the beginning, cemented hip replacements weren't very good. All right, this is before they came up with plasma spraying, and they started looking at porous metal coatings. And we've already talked about one of those, where you sinter a sphere onto titanium or sinter a sphere onto cobalt chrome, and you make this. You have the surface, and you have titanium sitting on the surface, and you form the neck. All right. And then the bone comes along and ingrows and goes underneath these particles and gets interlocking that way. All right? Yes? Oh, I'm sorry. Come on. Well, maybe it's not going to let me do that. There he goes. Okay. I pull the cartoon down. All right? You can see that now. And it's all very straightforward. It's just a initial process of sintering that forms those necks and gives you that coating that you want. And this is literally what it looks like in some of these products that they make. And so the idea is that these ingrowth surfaces, come on, have revolutionized the field of orthopedics. Biological fixation to host bone is achieved by direct osseointegration. There's that word again. And then move my cartoons around. Into load-bearing porous implants provided a pathway to address stress shielding problems involving porous tantalum. Do we know what stress shielding is? Joel?
Yeah, whenever you have a too hard of a substance that protects the bone in a certain place where it shouldn't, and then you get bone ingrowth where you don't want it?
You kind of get concentrations of bone where they shouldn't be and an absence of bone where it shouldn't be in the bone itself. All right. I'll give you a quick example, but you're on the right track. So you guys have heard of this before. So that's really what I'm trying to verify and make sure we're kind of on the same page. And so, these porous bead-based coatings, I just gave you this cartoon already, were heavily investigated starting in the 1970s, and it was developed for cobalt chrome and titanium bead processes, and is still used today. All right, exactly what I said before, beads sitting on surfaces, you form a sinter neck, and boom, you've got a product. All right, so everything we learned about sintering and transport and so forth applies to the development of these bead coatings on the surface. And from there, they tried to get fancy, and they made something called cancellous structured titanium. And so the target here is bone. This is what bone looks like, cancellous bone. All right, so cancellous bone is the inside of the bone. So when your dog chews on the bone, it's what they chew on the inside of the bone. The outside is cortical bone, which does most of the work in terms of bearing load. All right, so sometimes I see papers where they say, oh, well, our implant has the properties of cancellous bone. It's like, so what? Big deal. It's this crappy weak stuff on the inside of a bone. The cortical bone does the real work. But anyway, what they're doing here is they're trying to make something that looks like bone but is made out of titanium, all right, which makes sense. And what you can do is you can sinter commercially pure titanium at a high temperature and pressure onto a pre-existing titanium substrate. And what they do, and you can kind of sort of see it here, is you take that titanium, you put PMMA beads in it, which we just talked about a minute ago, PMMA, and you press that onto the surface, and then you burn away the PMMA. You leave holes behind where the PMMA used to be, and the titanium all around it. And then you do this sintering process, and so the titanium bonds to itself and allows for enhanced bone ingrowth. All right, so this was a big deal at the time, but it's kind of faded away because the properties of this, unsurprisingly to you, aren't all that great. All right, it's full of gigantic pores. So we know that its properties aren't very good. They could shear off, so we don't like it very much. Big deal for a while there. And there is still this technique of plasma spraying. I talked about it for hydroxyapatite, and you can plasma spray titanium too. All right, it melts relatively easily. And high temperature, focus them on a metallic substrate. You can get a bond formed, and you know its story now. It's these multi-layer structures that are kind of ugly when you cut them open, but it gives you titanium where you might want it to be, and it has some porosity, irregular with interconnecting pores. And so what you do is you take that process and you make it even uglier by making pores predominant in that structure. And so it is useful because you make these components, you have a solid piece of titanium, and then you put porous titanium on top of it with this technology. All right, and so this has been used. One of the key things that we haven't talked about is the fact that when you expose these things to all these high temperature processes, you start to worry about the implant itself. We're just putting coatings on things willy-nilly. What happens to the titanium? We have this wildly engineered piece of titanium we talked about over and over again, and you give it some more heat treatment. All right, you put something on its surface that wasn't there at the beginning, and so we have to worry about, does it maintain 90% of the fatigue strength that it used to have? All right, someone somewhere had to test that for millions of cycles to find out whether it was still as good as it should have been. And then higher than 50% for the sintered cancellous titanium. So it's better than that. And then, of course, perform as well or better, usually better, in order to justify actually doing it. And it's safe and predictable. We know what titanium does. And this is an example of the kinds of things they make. So that's obviously an acetabular component. What are those holes there for? Gigantic holes. Screws that do what? They screw into the acetabulum itself, all right? So you have a mechanical connection. They probably don't use every hole, all right, but they'll use some holes to make sure it stays in place. Again, motion is the enemy in this context. So they can do this for the acetabular cup. So this is porous plasma spray titanium on top of a solid titanium cup, all right. So the cup is there, it's solid metal, it's got the good load bearing. And then you have the polyethylene, and some of them have these pegs on it that are supposed to fit into these holes so the polyethylene doesn't move around, but it still gets loose. All right. This Iowa grant we had, big problem. The polyethylene can get loose, rattle around, and anyway, it's ugly. So, but this shows you what they can do with it. And those, what are those spikes for? Motion is the enemy. Also, it's grip. All right, it grips the bone. So they just jam it into the bone, spike it in there. All right. So every little bit helps. So, but they weren't very happy with that because the porosity of those sprayed coatings isn't really what they want. And so there's a goal here for metallic foams. And as you saw, they tried CSTI and didn't work out very well. Porosity is in the 30% range. Maximum bone growth is limited, and implant bone contact must be maximized. Cannot be used as bulk structural materials. And what we're talking about here is primarily CSTI because it was just terrible stuff. However, with tantalum and some foam materials, you can get a reticulated skeleton, and the characteristics of these materials are similar to that of cancellous bone, all right, which, as I told you before, is the weak part of the bone, but still good enough. And what happens is you get low modulus of elasticity favorable to bone ingrowth and bonding, and so we'll talk about that in a second. But this is an example of these commercial products that are out there. And they do exist. They are a reticulated structure. You saw an example of that before when we talked about the electron beam heating and laser heating and so forth, and shaping these things in these powder beds and so forth. So you can do that and generate these structures. And they're usually coatings, though. They're not really structural components themselves on top of a dense metal. And that's fine relatively well. But there's this new technology called trabecular metal. And it's made from not titanium, but tantalum, all right? So you go to this weird part of the periodic table where we don't normally venture, and you have this metal, which is body-centered cubic, all right? Relatively inert in vivo, all right? Tantalum is not a common material, so somebody gathered a lot of it and figured this out. And internally, at the microstructural scale, it's made up of repeating dodecahedrons, which can be made to resemble the structure of cancellous bone. And things are interesting. Pyrolysis of polymer foam precursor that gives you a low-density vitreous carbon skeleton, and then chemical vapor deposition infiltration of a commercially pure tantalum onto the scaffold. So again, on the right-hand side, we have the target structure, and then on the left-hand side, we have this trabecular metal. All right. So the scale is the same. We have similar pore sizes, and we have a metal now that we are proposing has good mechanical properties, unlike CSTI. All right. And how do we get there? How do we get these good mechanical properties? You've got the formation of a vitreous carbon skeleton. So you take, and we talked about this before, you take polymer, you heat it up in inert conditions, it doesn't volatilize, it makes carbon. All right, there's no oxygen there, and if you heat it quickly, then you don't let it tear apart itself. All right, and you can make carbon, or you can cross-linking it, and then it won't volatilize at all and makes carbon. So you take a sponge, heat it up, and you make this vitreous carbon skeleton, and it ends up being coated with the tantalum. And so this is zooming in here. You see this B phase is your vitreous carbon, and then the A phase on the outside of it is the tantalum, dense tantalum, by the way, sitting on the outside of that carbon skeleton. All right. So you make this preform. Again, a lot of organic sponges, you just heat them up. They make a very delicate carbon structure, and then you take that very delicate structure and you coat it with tantalum. Does everyone see that? That's what all that is. Very interesting process. You get crystallographic growth pattern on the vitreous carbon, and then the money part of this differs from all these other technologies in the high degree of its porosity, up to 80%. All right, nothing I showed you before was that high, and the regularity of its pore size and shape, and has been used in orthopedic reconstructions for more than a decade now. All right, because it's got these wonderful properties. All right, so now we have something that is porous, does have the properties that make it load-bearing because of the way this is made and the continuity of its overall structure. All right, so that's very significant.
What is the cost of that compared to titanium?
That's like 5 times as much, but who cares? You know, it's medicine. All right, you can pay for it. It's not as easy to make, for sure. I mean, you can't injection mold this stuff. That's a big issue. And one of the reasons why is it's necessary to make it using these CVI processes. Have you heard about CVI and CVD? Chemical vapor infiltration, chemical vapor deposition, right? Any of that? Yes? Sort of, maybe once or twice. And so there's this question of how do you make it? And it's easier, it's harder than it seems. So if this is our reticulated carbon skeleton, and we're bringing in, we are bringing in a gas that has our tantalum precursor in it. Come on, what is wrong with this thing? Precursor. So some kind of gas that has molecules that contain tantalum, and that gas hits this hot surface, all right, and as soon as it hits the hot surface, it makes tantalum. All right, that's the nature of this precursor. And everywhere else it hits the hot surface, it makes tantalum. All right, but the issue here is that you don't just want to treat the surface, you want to treat the interior, and what happens is you just keep depositing tantalum on the outside because that tantalum decomposes at the first hot surface it sees, not every surface that you're interested in. You want the entire skeleton coated. So what they have to do, and as it says here, eventually this seals off the interior from the exterior, you get a dense exterior and a porous interior. Whoops. Dense exterior and porous interior. So that's not good. So we work around this. Very novel idea. I hope somebody got paid well for this idea. You do the same thing in that you have your reticulated carbon skeleton in here, and you bring in the same precursor, and what's happening now is that rather than the whole thing being in the furnace, you've got this moving bottom, basically. All right, and so what happens is, as you heat the furnace up, this is at the low position, and you bring the gas in, and that gas stays cool until it hits that hot surface, and then it deposits tantalum again. All right, and you let that go for a little while, and then you inch this thing up by a couple of millimeters, and then the tantalum starts decomposing at the next hot surface, it seems, which is now moved into the skeleton. And you just keep repeating this over and over again until the entire thing has uniform tantalum deposition on it. All right, so a very cool process. I hope they paid somebody well, whoever did this. All right, and so unlike other foam structures, it has applications on hips and knees, high coefficient of friction, can withstand load, support bone ingrowth, corrosion resistant, used for all kinds of bony applications, not just acetabulate cups. And you get this wonderful occupation of pores with it new bone at 1 year, and high shear strength and the centered version of those beads, which of course is very important. You can use it for other types of tissues. You get good tissue ingrowth and blood vessels. All right, again, bone is alive. What you dog chews on is not, but bone is alive. Blood vessels are required to take away waste products and bring in food for these cells that make up the bone. And you get only one failure after 3 years, a 98% success rate, which is what doctors like. This is showing you, so this is the stress shielding thing. What you've got is the initial surgery, all right, and then 2 years post-operatively, you can see that the big screw holding everything in place. What you start to see, and then maybe you can see this, maybe you can't, but you start to see things look a little less dense in one side versus the other, and that's because this is not quite as white. So if you're an orthopod, you read these things in your sleep. But what you can start to see is that bone is going away because load is being carried by this screw, which goes straight to the acetabulum, and this bone starts to resorb. All right, because that's what bone does. It's under dynamic equilibrium involving stress. More obvious here, this is the normal femur, all right? Oops, before they Black and Decker it. All right, so they come along, they cut off the top of the femur, and you can see there's a certain density here, and then a certain different density there. After 2 years, 8 years, I'm sorry, all right, we still see a high density here, although it's not, it's down lower on the implant. And then up here, we have something that is starting to look not as mineral rich, all right? And so this means if grandma slips on the floor, then this implant can just break right through her femur if she hits the floor wrong, okay? Because it's really weak at the top. And this is why they put those porous coatings at the top of the femoral stem to make sure that bonding is good there and load transfer remains good, because they want it to be distributed, not concentrated like you see it here. That bone is very dense there, come on, very dense there, and not very dense at the top. All right, and that is bad news. And that is stress shielding, all right? The stress is bypassing areas of bone, osteoporosis in those areas. If it doesn't see stress, it starts to lose mineral density. And so we worry about stress shielding a lot. And so there's some comments about it being well fixed. And it's all fine and dandy. This is showing you the result of a trabecular metal. And you've got these wonderful structures. You can produce them with a polyethylene containing implant. And this is showing you bone ingrowth. Come on, bone ingrowth into something that was removed from a human. So the bone's growing in nicely. And it can be used in a lot of other areas of application. So it can be used in the shoulder as well. All right, shoulder problems can be very painful. And so they've used this in that context. And the strategy is the same as before. It's at the top of the implant. It's not the entire implant. It's just where you need to make sure bone fixation is good and stress shielding doesn't occur. All right. Again, stress shielding shields the bone. It weakens the bone when it's shielded from stress. And that's a bad thing. Again, grandma falls on the floor. All right, and it's used for other areas of applications on the total knee. Okay, sorry I ran over. Any questions about that? All right, So this is great stuff. It's much more expensive, but you know, the stress shielding issue goes away if you have a porous implant like that can bear load. Yeah.
So is trabecular metal usually used in the acetabular cup? Is that where it's usually used rather than the femoral component?
In the what?
The femoral component?
It's used, yeah, it's used in the acetabular cup, but it's also used at the top of the femoral component. So as you saw, it's kind of a coating at the top where that threat of stress shielding exists. You want bone to ingrow so it sees stress up there at the top. So when someone falls, that bone is not weaker than it used to be. Does that make sense?
Yeah.
Okay. All right, so I will email out that paper, not the whole thing, but just the pages of interest, and you guys can get to work on that. All right, so I'll see you on Monday for a review.